Alright, so we're going to start with a few more questions, just sort of reviewing what we did last time with trig and dimensional analysis units, all that business. So let's just go through these. There are about 15 questions, I think, maybe 20. These are multiple choice questions. I'll put the solutions up after we finish them in class. It'll probably be tomorrow before I put them up, though. But first, so if the displacement of an object x is related to velocity v, according to this relation, the constant a has which dimensions? Remember, displacement is in meters, velocity v is in meters per second, and acceleration is in meters per second squared. We'll get to that in chapter 2. Hey, Hunter. Kayla. Wayne. Guys, we just started these clicker questions. I'm going to stop in about 10 seconds. If you don't know, just guess. Stop at 1:45. Somebody missing a clicker today? Oh, no, there we go. Okay. Alright, let's see. Looks like, hey, Courtney. So we just want to put in our units for each variable. So I have x equal a times v. X is in meters, v is in meters per second. So I want to know what units here will give me the same on both sides. And what is that going to be? It's not a as most of you put, but it's what? Alright, if I put in seconds there, it cancels with that, and I'm left with meters on the other side. Alright, so C is the right answer. Guys, these questions are meant to help prepare you for the multiple choice part of the exam. The multiple choice part of your exam on the 10th will be mostly conceptual. It'll be questions a lot like this. In fact, you'll see some questions. You might even see some of these just verbatim, but you'll see certainly questions that are a lot like these questions, okay? That are testing sort of conceptual knowledge of what we've been doing. All right. Dimensions of a crate are 1 by 1.2 by 0.8. They're 3.28 feet per meter. What is the volume of the crate in cubic feet? You should be able to do this without your calculator. You should be able to look at it and figure out what the answer is. Try to do that first. If you need your calculator, that's fine. But try to estimate it first and see if you can find the answer. About 15 more seconds. Stop at 1:40. It's 10 seconds. I'm going to stop at 1:38 now. Are we at 15 now? We do. Alright, let's see. We're sort of split between A and D. This is roughly a 1 by 1 by 1 meter block, right? So it's about this big, a 1 cubic meter, and there are roughly how many feet in a meter? Roughly how many feet? They're roughly 3, right? A little more than 3. So we just say 3 times 3 times 3. Right, so this cubic meter is 3 by 3 by 3 feet, and so that's estimated to be about 30 cubic feet. Right, so you could just say, I'm going to round off my ones, 1.2 and 0.8 to 1 meter, and then I have a 1 cubic meter block, and then I know there are roughly 3 feet in that. 3 by 3 by 3 is a rough estimate. Now, if you wanted to, so the answer is A, 34, which is the closest to 30. If you actually want to run the numbers, you would say 1 times 1.2 times 0.8. What is this thing? It's like 0.96, is that right? Somebody do that? It was 0.96. Yeah, so 0.96 cubic meters. And then notice I kept 2 sig figs because I had 2 sig figs all throughout. And then if I wanted to convert that to cubic feet, 0.96 cubic meters. In 1 meter, there are 3.28 feet. And then the problem that many of you had if you put D is you probably didn't cube that. D is not the right answer. You have to cube this whole term. And when you do that, you get 34 cubic feet. Is that what you did if you put D? That's like the next best wrong answer, right? So, but A is the correct answer. You will probably, very likely to have a cube or a power conversion like that, where you have to convert units with power. So make sure that you're up to date on that. There are some examples in the homework. All right, if a jet airplane declines at an angle of 15 degrees with respect to the horizontal and follows a straight line path for a distance of 400 meters, how much altitude does it gain? The words might not make sense here. Let me draw a picture. That means that the airplane starts here and ends here, and it travels 400 meters. That's what it means by a straight line path. It travels 400 meters at an angle. Now I know the altitude that it gains. Remember your trig functions. We'll use those a lot this semester. So. About 10 more seconds. Stopping at 125. On the test, you want to be able to do these in a minute or less, so make sure that it'll help with practice. So we have 636. So we have 16. Let's see here. So my angle is 15 degrees. This is just a right angle trig problem. 15 degrees here. I want to know this h, and so I say, which trig function do you want to use? Right, I want to use the sine. That's opposite over hypotenuse, so sine of 15 equals h over 400. Is it 100 if you do sine of 15 times 400? What is it? 103. Okay, so h equals 400 sine of 15. Which is Josh, right, Josh? Yeah, it's 103, but rounding to just 1 sig fig is 100 meters. So that's going to be the right answer. Good job. Make sure you're up on your trig. We're going to use a lot of trig in chapters 2 and 3 and on chapter 4. And if you don't get right angle trigonometry right now, then you're going to really need it. So if you're having trouble with it, please come see me. If you don't get it now, it's going to be a big problem later. All right, mass along with those other 2 quantities make up the 3 basic quantities that we use. Mass, what, and what? 15 more seconds. Stop at 30. Somebody else out there? Alright. Okay. In our SI system, we have for mass, remember our unit was, they were trying to make that sphere, and then we had a length, which used to be the bar, but now it's what? Do you remember the standard for length?
The distance light travels.
That's right, Harley, very good. So it's the distance that light travels, and then we have time, which is based on a particular atom. What was it? Do you remember? Cesium, right? The frequency of the cesium atom. So mass, length, and time. And those are our basic quantities in mechanics. Now we have some other basic quantities, the basic SI units, that we'll use next semester. Things like to measure the brightness of light, measure charge, all that jazz. But for now, we're just dealing with mass, length, and time. Okay, B and D are both derived quantities, so we'll use mass, length, and time to derive power and force. All right, we'll get into those this semester, but they're sort of made out of mass, length, and time, and we'll see that as we go along. All right. You have this expression, y equals x squared. Which of these then is true about that expression? You'll see as we go through the semester that I'll ask us a lot of sort of relational questions like this, like if you change one variable, what happens to the other? Which of these statements is true about y equals x squared? It's to always be true, necessarily true. It's about 10 more seconds. I'll stop at 45. 45. Okay. I always find it easy to put in numbers, easier to put in numbers here. And so if I have y equals x squared, for the first one, if I put in, say, 2y, if I put in a 2y, that means that x is going to increase by root 2, because root 2 squared is 2, and that would make the equation the same. So A is not the right answer. All right. Y can be greater than x, but not necessarily. Like, for example, if x was equal to 2, then y would equal what?
4.
It would equal 4, right? 2 squared is 4. But if x was, say, a half, then y would be 1/4, which is actually smaller. So B is sometimes true, but not necessarily true. Not always true. If x is less than 1. If x doubles, then y doubles. That's called a linear relationship, where if you change one variable by a certain amount, the other variable changes by that same amount. But this is not a linear relationship. What type of relationship is this? It's a quadratic relationship, right? So it's a parabola, right? So that leaves D, that if x doubles, then y quadruples. So if I have y equals x squared, imagine that if I double x, then I get a quadrupling of y. All right. Probably not going to see a question like this in this next exam unless it comes up in chapter 2. But all throughout the semester, we'll see questions like this, where you'll know a certain relationship, say between force and acceleration, or distance and time, and I'll ask you what happens if you double the time, or what happens if you have the distance, or things like that. And you'll have to think back to what the relationship is, and then determine how that other variable is affected. It's a big thing on standardized tests, and so that's why I sort of emphasize it here. So it's not just a skill that's related to physics, but other things too, like if you go on and take the GRE or the MCAT or whatever it is that you're taking. So it's important for a standardized test, and it's important for you to just understand the relationship. All right, so D is the right answer. Okay, which of these is dimensionally consistent with 1 over seconds? 1 over seconds. Remember, V is meters per second, X is meters, and Z is seconds. Which of these has units that are equivalent to 1 over time, or 1 over seconds? This is supposed to be a lowercase v right here. It's not volume, it's velocity. Alright, just a few more seconds. I'll stop at 1:30. Looks like we have one person out there. Hasn't clicked in. Or two people maybe. Somebody else come in? 2, 5, 8, 11. Hey, we have 17. Well, y'all keep trickling in, huh? Alright, let's see what we got here. A is the right answer. Very good. You just want to write in the units like we did before. So V is meters per second. And then X is meters, but it's in the denominator, so I like to write it like that. And so then the meters cancel, and I'm left with 1 over seconds. On the exam, you will have a dimensional analysis, and it'll be likely the multiple choice. You might have a couple actually. This is a useful skill just for you to carry on through the semester. In general, whenever you're doing like a math-based science, it's useful to look at the units. Because if you have the units wrong, you definitely have the answer wrong. And if you have the units right, you probably have the answer right. Not always, but probably. All right, which of these is the standard for time? I'm going to stop at 20 seconds. 20 seconds. Give you till 25. All right. Okay, very good. Remember, it used to be based on the solar day, but not anymore. Like, that was 100 years ago or more. Okay, so now it's based on the frequency of the cesium atom, and that allows us to have very accurate timing, which is important for communications primarily, but for other things as well. Measuring very small intervals of time. All right, since 1983, the standard for the meter has been which of these? So the current standard for the meter is what? Stop at 25. Okay, very good. And which of these is consistent with acceleration? Velocity is meters per second, distance is meter, time seconds, and acceleration is meters per second squared. So which of these is meters per second squared? Remember, you can ask your neighbor what they've got, or talk to them about it if you like. Just a few more seconds. I'll stop at 1:30. Okay, it looks like we're sort of split between C and D. why don't you turn to the person on your right, except for this row, like these two rows, these two, and these two, and I'll see what you got, and then try to decide between C or D. It is either C or D, but turn to the person on your right and ask them. And Harley, you can join with Cole there. So you guys, and then you folks, just turn to the person on your right. Ask what you put. You two ask what you put. It is either C or D, so when you decide on an answer, go ahead and click that in. Michaela, you got in on that? I want 100% on this one. Alright, it's about 10-15 more seconds. Stop at 1:05. So go ahead and click in your new answer, or it might be your old answer. It's fine too. It is either C or D. Stop at 1:10. Alright, D is the right answer. I just put in our unit, so V is meters per second, but it's squared, so it's meters squared per second squared, and then X is meters, so that's 1 over meters. And so that cancels with that, and leaves me with meters per second squared. But C, let's just go ahead and do C, I'm not going to do them all, but C is meters squared per second squared, like that. But then the time looks like this, which leaves me meters squared per second cubed, which is an acceleration. I don't know what that is, it's something else. Okay? Alright. Important skill. Alright, which of these points is nearest the y-axis? Think back our Cartesian coordinate plane. What value has to be small to get as close to the y-axis? Alright. You can ask your neighbor if you like. Just about 5-10 more seconds. Go ahead and turn to your neighbor and ask them what they put. Just verify yours. Alright, I'll stop at 55. 55. Change your answer. Go ahead and do it now. Okay, very good. X has to be small to get up close to the y-axis, right? On the y-axis is x equals 0, so whatever has the smallest x value. Good job. We should do tests like this, right? Where you talk to one another. All right, which one of these gives proper sig figs? Now you don't have to do this in your calculator, because if you put it in your calculator, you're just going to get this. All right? But which of these is proper for sig figs? Multiply numbers, and you can talk to your neighbor. I recommend it. All right, let's stop at 45. 45. Okay, excellent. So when multiplying, you keep the lowest number of what? Significant figures, right? So it's going to be 2 sig figs, which is A. And the speed of a boat is given in knots. The speed of 5 knots were expressed in a system of the SI system. The units would be what? A knot is a knot. Well, never mind. It's a speed. If it were the SI system, what would it be? What units would it be? Share your answer with your neighbor, please. Alright, so I'm going to stop at 40 seconds. 40 seconds. Excellent. Hey, did you hear about the guy? He lost his entire left side, like in an accident. His left arm got cut off. His left leg got cut off. Did you hear about that guy? I'm serious. Yeah, he's all right now. You get it? He's all right. Because he only has right arm, right leg. That's because you got 100% on your clicker question. So that was well earned. Very good. Okay. Another dimensions. I think this might be the last one. No, we have one more after this. A is meters per second squared, V is meters per second, X is meters, and C is seconds. Which of these is not correct? Which one is not dimensionally correct? You get good at this, you probably should be able to look at it itself. When you get an answer, please turn to your neighbor on your right. Thomas. Courtney, did you share your answer with Cole? Or have you got an answer?
Yeah, and she's still share about it.
Okay, I'll share. Is that time to get up? Is it? Uh-huh. You guys. Alright, I'm going to stop at 145. Just go ahead and guess if you don't know. Alright, C is correct. Or incorrect as it may be in this case. I have meters per second. A is meters per second squared. And then T is 1 over second. So notice I have meters per second on one side, meters per second cubed on the other. And so that is not correct. All the others are correct. Let's just do one like this one. I'll do this one right here. I have meters per second squared. Meters per second squared. They're both squared because V is squared. And then 1 over meters. So that cancels with one of those and gives me the same units on both sides. Right. So you'll certainly see one or two of those on the test, but like I said, it's just a useful skill for you to carry through. And I think this is the last one. All right, here you're adding numbers. Which one is the correct way to express it? Again, you don't need your calculator because if you put in your calculator, you get A. But what's the appropriate way to record that number? All right, I'm going to stop at 40 seconds. Just guess if you don't know. Okay, D is the right answer. When you're adding and subtracting numbers, you keep the lowest number of what? Decimal places. And the one with the lowest number of decimal places here is 15, with no decimal places at all. And so the answer is going to be 58. All right? All right, good. That's the end for that. I will be putting this up on the website, so just to remind you where that is. If you go to our website, under concept test right here, it'll be linked here under chapter 1. There's nothing there now, but I'll put it up. It'll probably be tomorrow before I put it up though, okay? that's a useful way to help you prepare for the multiple choice part of the exam. Just going through your notes too and just sort of going over the basic knowledge. So in that multiple choice part of the exam, you have questions like this that are sort of conceptual based, and then also just questions about information, right? Like what are the standards, like somewhat like what we had here. So that's a good way for you to prepare for those 30 points of the exam. All right? It's a small part, but it's not insignificant. I mean, it's 3 letter grades, right? The multiple choice part. We're going to carry on into chapter 2. I realized chapter 1 was kind of fast, and in fact, chapter 2 we'll sort of go through in about the same amount of time. Chapter 2 is going to be linked together with chapter 3. They're sort of related topics, because chapter 2 will deal with motion in 1 dimension, or 2 dimensions, and chapter 3 will deal with motion in 2 dimensions. So they're very closely related. And then actually from there on, all the chapters are going to sort of be linked together in one way or another. But chapter 2 is on motion in 1 dimension. We call this study the study of kinematics. So kinematics is just the study of motion. In particular, we'll look at the motion of objects. We'll look at their position or their displacement, the distance that they've traveled. We'll look at their rate of change of position. We call that velocity. And then we also look at the rate of change of velocity, which we call what? Acceleration, right? Does anybody know what the rate of change of acceleration is? This is just a little trivia for you. It's kind of cool. Kind of press your friends. The rate of change of acceleration. That would be like meters per second cubed. I know what that is? $5. $5, but do I know? It's called jerk. Jerk. Right. So you have displacement, velocity, acceleration, jerk. And each is the derivative of the next. So like velocity is the derivative of position, acceleration is the derivative of velocity, and jerk is the acceleration of acceleration, is the derivative of acceleration. Right, so you're going to tell your friends over lunch, boy, my acceleration was changing a lot when I was driving over to school. I had a very high jerk. They'll be impressed. All right, so frame of reference. This just, you set the coordinate system and your origin. Your frame of reference sets the coordinate system. And the origin. And you answer the question, from where are you observing the motion? Two points on this is that you can set your coordinate system at any point, really, and we can set our origin at any point. And in fact, when we get into chapters 2 and 3, we'll take our coordinate system and we'll do funky things, we'll rotate it and all that jazz. It just makes our problems easier to work. And you can set your origin anywhere you want. That's something that's completely up to you. And then also from where you're observing the motion, you can observe the motion from a stationary frame of reference. So it's like you're standing still, or you can observe your motion from a moving frame of reference. So for example, if you're driving in a car and somebody pulls up next to you, you're both moving, right? So you both have a certain velocity, but it appears that the person next to you is not moving at all. And that's dependent upon your frame of reference. But if you were standing on the side of the road, it would appear as if that person were zooming by at 50 miles an hour or whatever. Okay? In this class, I think always we'll be from a stationary frame of reference. That means like we'll be the guy standing on the side of the road. Okay? So in kinematics, we consider displacement, velocity, and acceleration. And I'm going to define each of these. They have particular definitions that might go beyond just sort of what you think of what they are. So first of all, displacement is just the change in position. So this is our definition for displacement. It's going to be our final position minus our initial position. See, I don't think I have the Seabiscuit clip. Let me see. Pretty sure I don't have it. Oh yeah, I have it. Y'all want to watch it? It's kind of cool. It's not terrible. It is sort of relevant, but this horse traveling around this track. It's a 1 mile track, I think. Is that right? I'm pretty sure it's the case. If I have this horse traveling around this track, there's my horse. He travels around. What is his displacement when he travels around the track? A 1 mile track. It's going to be 0, right? So the point here is that it's not a measure of the distance that he travels, but it's a measure of his initial minus his final position. Right? So the displacement is just the difference between his final and initial position, as it's defined here. So here our displacement delta x will equal to 0 because he begins and finishes at the same point. We'll also define distance here. I think it's on the next page. Yeah, we'll talk about it in just a second. So for example, if I have, if I set up my coordinate system here, and I say this is 0 meters, and then this isn't quite 1 meter, but let's say it is 1 meter, and this is 2 meters, and I'll call this -1 meter. If I start here and move here, what's my displacement? 1 meter, right. And if I start here and then move here, what's my displacement? It's not 1 meter. It's going to be -1, which is my final position, minus 0. So in this case, my displacement, delta x, is equal to my final position, that's -1, minus 0 is -1 meters. Right? Now if I start over here at 2 meters, and I travel in this direction, what is my displacement? I started at 2, I came to -1. It's not just 3, it's -3, right? So it's true that I did travel 3 meters, but my displacement here will equal to my final position, that's -1, minus my initial position, which is -3 meters. Right? So if I travel from 1 to -1, what's my displacement? -2. If I travel from -1 to 2 meters, what's my displacement? +3, right? So if I travel 2 meters is my final position, minus -1, that's equal to +3 meters. All right, what I'm doing here is we're expressing what we call a vector quantity, which we'll define in just a second, but a vector has a magnitude and a direction. It has a direction, and then it also has a value, like an actual numeric value. And what I'm doing here is I'm expressing a vector quantity, giving its direction and its magnitude. So the number represents the magnitude of your displacement, and the sign of this number in one dimension expresses the direction, right? So a positive direction is in what direction? Left or right? It's to the right. That's our right-handed coordinate system. And then a negative number expresses a left direction. All right, in the next chapter we'll express direction with angles and all that business. But so if you want to write this down, you could have a 0, -1, +1. And if I start here, for example, and move in this direction, my displacement is -1 minus -1, or excuse me, minus +1. And so that's going to be -2 meters. All right, so my displacement here is -2 meters. But if I start, say, right here and go to there, then my displacement is +1 minus 0, which is +1 meters. So as I said, displacement is a vector quantity. And vectors have both magnitude and direction. In Chapter 3, we'll deal with direction more rigorously, but in this chapter, we're just going to deal with a one-dimensional coordinate system. So our direction is either going to be positive or negative. So in this case, let's say that we had delta x equal to -2 meters. My direction is negative, or in our right-handed coordinate system, left, and my magnitude is 2 meters. And sometimes we're going to give direction. In the next chapter, we'll give it in other ways. So we'll use our cardinal directions, north, south, east, and west. Sometimes we'll also give it as up or down. Now, north is positive, south is negative, east is positive, west is negative. That's in our right-handed coordinate system, right? If you draw your cardinal directions, north, south, east, and west. What's your mnemonic to remember that? Y'all remember from first grade? Never eat soggy waffles, right? NESW. Up and down is positive and negative. Left, right is negative and positive, right? So that's in our right-handed coordinate system. And as I said, in the next chapter, we'll use angles to express direction. We'll also use vector notation, IJK notation, which we'll define later. All right? Give y'all just a second. All right, can I go down from here? Yeah? All right. Some examples of vectors that we'll deal with. Displacement, velocity, and acceleration are all vectors. We'll deal with a lot of other vectors as well. So forces are vectors, momentum is a vector. We'll deal with a lot of different vector quantities. Vectors are pretty important to physics and general classical physics especially. And so we'll deal a lot with vectors. And we'll get into that in the next chapter, dealing with vectors more so. We usually show variables for vectors with an arrow. I'm not real rigorous about this, so sometimes I might sort of lapse out of it. But usually we show them, for example, as an x with an arrow over it, or for velocity, v with an arrow, a with an arrow. A force vector has an arrow over it. So that's the correct way to write a vector quantity with an arrow over it. Sometimes you'll draw a vector with a little hat on it, and we'll define unit vectors, I think in the next chapter, but you can also write them like this. So a little hat, you might see that as well. I, J, and K. We'll define what those mean later, but they're a type of vector that have a magnitude of 1. All right. Scalar quantities. Vector quantities have a what and a what? Magnitude and direction. So scalar quantities have what only? No, not direction, only magnitude. So scalar quantities are just the magnitude of the vector. So scalar quantities only have a magnitude. They have no direction associated with them. Now we have some scalar quantities that are associated with our vector quantities. So the scalar quantity associated with displacement is distance. All right, and distance would be, if it was in this case, it would just be 1 meter, not negative 1 meter, and it would just be 3 meters, not negative 3 meters. And here, you would just list it not as positive, but just 3. It doesn't have a direction associated with it. There's no sign. It's just a magnitude or value. We also, for velocity, we have speed. That's the scalar quantities. What are some other scalar quantities that we measure? There's some scalar quantities. These are physical quantities that you measure that don't have a direction associated with them. Think of some physical quantities? We talked about them. Mass is a scalar quantity, right? No direction associated with mass. What else? Time is a scalar quantity, right? That's good. No direction. I mean, you can sort of maybe say maybe it doesn't have a direction, but it is a scalar quantity. Somebody else? Another scalar? Mass, time. Let me write those down. They're a lot actually. Anything else? Area and volume, right? Those are both scalar quantities. Charge is a scalar quantity. We'll get into that next semester a lot. Yeah, so those are the scalar quantities. Let's try this little quick test question. could have something like this in the multiple choice part of the exam. And by the way, you guys realize I just pulled these from old tests. So these quick test questions, they were just old multiple choice test questions. And then later we'll do some free response questions as well. So which of these is or are a scalar quantity? And remember this, I like to do these kind of questions where I use multiple options, and then one or more of them can be the correct answer. And so you have to pick which that is. So which of those is a scalar quantity? All right, I'll stop at 45. Still missing a couple folks. That has to be right. Let's see, C, 1 and 3. What's that noise? Is that outside? I think he was just sneezing. Yeah, 1 and 3. So mass and speed are both scalar quantities. Very good. Okay, so speed is a scalar quantity, as I've already said. It is the magnitude of the velocity. And we have some definitions for speed. First of all, the average speed is the total distance divided by the total time. Or we could also just write it as d over t. So this is what we usually think of when we think of speed. It's just our rate of change of the distance divided by the time. And so if I have a runner that runs around a 400-meter track, and we're not talking about displacement here, I'm talking about a distance. And if you run around a 400-meter track, what's the distance that you've traveled? 400 meters, right? It's not this whole business with final minus initial. And so our average speed would just be 400 meters divided by 60 seconds. And so that's 7 meters per second, roughly. And the distance covered here would be 400 meters. But the displacement around this 400-meter track would be what?
0.
Would be 0. Right, because it's a circle and my initial and final positions are the same. So there is a difference between distance and displacement. Distance is the distance that you travel, and displacement is just the difference between your initial and final position. That's a subtle difference, but it's a difference nonetheless. All right, let's see. Let's do this last thing on average velocity. We're going to define average velocity, and this will be important for later when we get into instantaneous velocity, which will be next time, because we base our definition of instantaneous velocity is the derivative of the average velocity. So average velocity is defined as delta x over delta t. These would be vector quantities, so to be correct I should draw an arrow over them. And so that's going to be my displacement over my time, which is x final minus x initial, divided by my total time, which is t final minus t initial. For the sake of this class, t initial will almost always be 0. So our t final is our total time. Average velocity is a vector, as I said. It has both magnitude and direction. And so the average velocity of the runner in the previous problem had a average velocity of what? The 400-meter track lady goes around a track. What's her average velocity? What's her displacement? Is 0. So her average velocity then is equal to 0. Because her displacement was 0, the units are in meters per second. We've already seen that bit. Let's see. Why don't we stop there before we'll get into the graphing and stuff next time. All right, so remember our exam isn't that far away. We just have maybe like a week and a half or so. September 10th, right? Is that right? What's today's date? Today's the 25th. Okay. We have a couple weeks. That exam will likely be all of chapter 1, all of chapter 2, and part of chapter 3. Probably the vectors part of chapter 3. Alright. You all have a good day. I will, if you have any questions, please come see me. I'll be around.